we studied different types of titration curves. We studied the titration curves of acids, weak acids or strong acids. We studied the titration curves of bases, weak bases and strong bases. We studied the titration curves of polyprotic acids, and we had the example of phosphoric acid. We studied the titration curves of polyfunctional bases, and we had the example of sodium carbonate titration curve. Now we will study the titration curves of mixtures of acids or bases. What do we mean by a mixture of acids or bases? We mean that the sample is not a single acid or a single base. It is composed of more than one acid or more than one base. For example, a sample composed of a mixture of acetic acid and HCl together in the sample, acetic acid and HCl, and ask you to analyze this sample or to determine the concentration of acetic acid and HCl in the sample, okay? Or to draw a titration curve for the titration curve of this titration, the titration of this sample containing both acetic acid and HCl, for example. Of course, the titration curves of mixtures of acids or bases the sample contains either acids or bases, not acids and bases together in the same sample, but either mixture of acids or mixture of bases. Otherwise, neutralization will occur within the sample, and this is not correct. Okay? The sample here is a mixture of acids or mixture of bases. Okay. Mixtures of acids or bases can be titrated stepwise if there is an appreciable difference in their strengths. There must generally be a difference in Ka values of at least 10 to the power minus 4. What do we mean by the word stepwise? Stepwise titration, that is to say, we have different separate breaks. Each break is corresponding to certain acid, and it has its independent endpoint. Okay, if we have stepwise titration, that is to say, we can see on the titration separate breaks, separate inflection. We mean here by the inflection the vertical part in which I can see the equivalence point, and I can use a proper visual indicator to distinguish and detect the endpoint. So when we have stepwise titration, we have these separate steps, these separate inflections, these separate breaks, whatever we call it. We can understand that we have separate endpoints, okay, for each determination in the mixture, okay? When we have these separate steps or breaks, we can obtain these separate steps if there is an appreciable difference in their strengths. That is to say, we have significant difference, appreciable difference, clear difference, okay? Clear difference, big difference, significant difference between the strengths of the two or more acids in the mixture, in the sample. There must generally be a difference in Ka values of at least 10 to the power minus 4. If the difference in K values is less than this value, is less than 10 minus to the power minus 4, that is to say, the two strengths are near each other. They are similar in strength. In this case, we will obtain stepwise titration? Of course not. Of course not. The two acids, or of course the two bases, will react together. They will go together. And on the calibration curve, I will see only one break corresponding to the total response of the two acids. or the two bases. I will see only one break. I cannot distinguish between the reaction of acid 1 and acid 2, or base 1 and base 2, of course. Okay? But if there is a significant difference of at least 10 to the power minus 4 between the two Ka, in this case, I will see two separate breaks, two separate inflections. Each inflection has its equivalence point, okay? And each inflection is corresponding to a step in the titration, to the reaction of one acid, okay? If one of the acids is a strong acid, a separate endpoint will be observed for the weak acid only if Ka is about 10 to the power minus 5 or smaller. For example, if I have a mixture containing, for example, strong acid like HCl and any other weak acid, if this weak acid, its Ka is larger than 10 to the power minus 5, larger than this value, in this case, it is weak acid, but its strength is not very, very weak. It will be similar somehow and near somehow to the strength of the strong acid. Okay, if it has a large Ka value, larger than 10 to the power minus 5. In this case, I will not distinguish a separate endpoint for the weak acid, but I will see one break corresponding for the total response, the strong acid and the weak acid together. And I cannot have stepwise titration in this case. When I have stepwise titration for a mixture containing a strong acid and a weak acid, only if Ka of the weak acid is about 10 to the power minus 5 or even smaller. Okay, in this case, I will have separate endpoints, because in this case, the difference between the strengths of the strong acid and this weak acid is large, is significant, is clear. Okay? The stronger acid will titrate first and will give a pH break at its equivalence point. Of course, when I begin the titration of a sample containing a mixture of two acids or more, the stronger acid will titrate first. Whatever here the stronger acid is the strong acid, HCl for example, or even if they are all weak acids, the stronger relatively, they are two acids, acid A and acid B. The two are weak acids, but one of them has higher Ka value. So it is relatively stronger than the other acid. Okay? In this case, the stronger acid, as we said, either it is a strong acid or it is a weak acid, but relatively its strength is higher than the other one with it in the mixture. The stronger acid will titrate first and will give a pH break at its equivalence point. This will be followed by titration of the weaker acid and a pH break at its equivalence point. Okay? The titration curve for a mixture of HCl and acetic acid versus sodium hydroxide. This example shows the titration of a sample composed of a mixture of HCl and acetic acid. I prepared this sample by taking certain volume of HCl of certain concentration and mixing this volume with a certain volume of acetic acid of another concentration or certain concentration. I mix these two volumes of HCl and acetic acid in a bottle or in flask, and I obtain this sample. The sample is composed of a mixture of HCl and acetic acid together in the same container. Okay, I will make the titration against sodium hydroxide titrant. We look to the titration curve. Here the titrant is sodium hydroxide. The sample is acidic, so I begin the line of the titration curve from below, from the acidic side, from low pH at the beginning because it is an acidic mixture. So the pH will be a low pH, below 7. Okay. I will follow up the titration curve. I will see two breaks. Two breaks. The first break will be for the stronger acid in the mixture. We just explained that when I have a mixture of a strong acid and a weaker acid, the strong acid will react first. He is the stronger. He will react first. So the first break will be corresponding to the reaction of HCl. The first break will be corresponding to the neutralization reaction of HCl using sodium hydroxide. Okay? The indicator of choice for this first break will be methyl orange because it is in acidic side. It falls in the acidic side, so the proper indicator is to select an indicator changing its color in this area. So I will select the methyl orange. We continue to follow the titration curve. We will see a second separate break. We will see a second separate break. The second break, supposing here we are working in the same conical flask. We didn't change the portion of the sample we work with it. احنا بنشتغل دلوقتي على نفس الكونيكال فلاسك. We are working on the same conical flask. We put methyl orange indicator and we found endpoint 1. Then on the same conical flask, we add the second indicator, the phenolphthalein, and we will follow up the change in the color till we distinguish the second endpoint. Okay. In the second endpoint here, what is remaining in the solution? Who will react? Who will react? All the HCl has finished its work and it gave the endpoint 1, the first break. Now I have in the solution the acetic acid still didn't react. It's still present and it didn't react. So in the second break, the acetic acid will do its neutralization reaction. Its proton will react and it gives me the second break. And the second equivalence point will be corresponding to the acetic acid content in the mixture. To select a proper indicator for this second step, I will select an indicator changing its color in the basic side. So the proper indicator here will be phenolphthalein. Of course, using different indicators on the same sample in the same conical flask, the color change will not be the same as we use single indicator in separate conical flask. Okay, here the phenolphthalein color will be, of course, affected by the presence of the background color of methyl orange already present in the conical flask. But no problem. I will distinguish the color. The first color change will be an indication of the second endpoint. Okay, no problem. All I want to know is that when the sample is a mixture of acids, the stronger one will react first. It will give me a first break. Then the weaker one will react second with a separate break if the requirements is fulfilled. And here the requirements of fulfilled, of course, the difference in strength between the HCl and the acetic acid is very big. HCl is a classical strong acid, and acetic acid is a classical weak acid. The strength is far away different from each other. So I will obtain the two separate breaks, and each break has its own indicator. The first break methyl orange, the second break phenolphthalein. The first break will be corresponding to HCl content. The second break will be corresponding to the acetic acid content. Okay. Let's see together some characteristics of the titration curve of the mixture of HCl and acetic acid sample versus sodium hydroxide. How many breaks can we see in this titration curve? This titration curve shows two breaks. This titration curves shows two breaks. The first one corresponding to the HCl content, and the second one characteristic or corresponding to the acetic acid content. Okay, first one we can use with it methyl orange indicator, and the second one we can use with it phenolphthalein indicator. Okay. At the equivalence point for HCl, the first equivalence point at the first break, a solution of acetic acid and sodium chloride remains, and so the equivalence point is acidic. What is the meaning of this sentence? At the equivalence point, what I have in the solution? I have the acetic acid already a component of the mixture of the sample, which already present in the sample, but it didn't react yet. So it is present in the sample, the acetic acid. And I have the sodium chloride. From where comes the sodium chloride? The sodium chloride will be produced from the reaction of HCl with sodium hydroxide. It will give me sodium chloride and water. HCl plus sodium hydroxide will give sodium chloride, salt, and water. So in the solution now, I have sodium chloride, which comes from the reaction of HCl, and acetic acid, which is originally present in the sample. Okay, so the pH of the first equivalence point is neutral. No, it is acidic pH. Why it is acidic? Due to the presence of acetic acid in the sample. The acetic acid already present in the solution will make the first equivalence point acidic pH. It is of acidic pH. If it was as a HCl sample alone without acetic acid, if I compare this curve to a titration curve of an HCl sample, pure HCl sample, the equivalence point will be, it will be neutral, because at the equivalence point, the solution will contain sodium chloride and water, and sodium chloride pH is equal to 7. Okay, but here in this mixture, the equivalence point pH is acidic due to the presence of acetic acid, okay, in the sample. ماشي. Okay. Beyond the equivalence point, the acetate-acetic buffer region is established. Acetate-acetic buffer region. As we studied before in the titration curve of acetic acid, once the acetic acid begin to react with the sodium hydroxide, part of the acetic acid will be present or will be transformed to acetate salt, and the remaining is not reacted yet. So I will have a mixture of acetic acid and acetate salt. Together, they form a buffer region. And this buffer will suppress the pH break for HCl. It will help to make the first step, that of HCl, more acidic. So the first equivalence point in this mixture is having an acidic pH due to the presence of acetic acid in the solution, and also due to the formation of the buffer region of acetate, which will markedly suppress the pH break for HCl, because it will resist the change in pH. It will resist the increase in pH. So it will further suppress the pH break for HCl. The remainder of the titration curve is identical to the titration curve of acetic acid. الجزء بقى اللي فاضل من التيتريشن كيرف هو زي التيتريشن كيرف of acetic acid. We just said the main characteristics of this titration